Hi, I hope you all had a great weekend. So we're going to jump in and start to continue section 4.4. I'm on page 281. The value f of c that we found in the mean value theorem is called the average value of f on closed interval ab. So if f is integrable on ab, then the average value of f on ab is defined to be average value is 1 over b minus a times the integral from a to b of f of x dx. This is just the formula, and we're going to do several homework questions with it, so go ahead and pause and write that down, and then we'll do example 4. So they want us to find the average value of f of x on the closed interval 1 to 4. So the average value is 1 over b minus a times the integral from a to b of f of x dx. So that is 1 over 4 minus 1, remember a and b, times the integral from 1 to 4 of 3x squared minus 2x dx. So that is 1/3 of, now let's go ahead and integrate. That's 3x to the third over 3 minus 2x to the second over 2. And we'll evaluate that from 1 to 4. Simplify that a little bit. That is just x third minus x to the second from 1 to 4. So I'm going to leave the 1/3 in front of everything while we evaluate. So we're going to do 4 to the third minus 4 squared minus 1 to the third minus 1 squared. So that is 1/3 times 64 minus 16 minus 1 plus 1. So that is 1/3 of 48, which is 16. So the average value of the function on the interval 1 to 4 is 16. Alrighty, and then if you'll all turn in your book to page 282 and look at example 5, we're not going to do this by hand, but this is an interesting problem. It says the first person to fly at a speed greater than the speed of sound was Charles Yeager on October 14th, 1947. And so you can read through that. He's the first person to have broken the sound barrier. And then if you look at example 5, at different altitudes in the Earth's atmosphere, sound travels at different speeds. The speed of sound, s of x, in meters per second, can be modeled by this complicated piecewise function. It's got 5 different pieces depending on the altitude that we're at. So 5 different portions of the graph, if you look below, depending on the altitude. So it's kind of an interesting problem. And if we were to integrate it, we'd have to integrate each of those 5 little parts, as you see down there in the solution. So you'd have to break it up from 0 to 11.5. We'd have to integrate that part, and then 11.5 to the 22. And then to get the final answer, we would add all of those up. And I don't know if you remember, but we had talked about how adding up the areas of the rectangles was an accumulation concept. Like we're accumulating these areas, we're adding them up. So finding the different, is it speeds? Yeah, finding the different speeds would be accumulating them and adding them all up in order to find the average speed. So at the very, very bottom, the average speed of sound would be that b minus a, 1 over b minus a. So 1 over 80 times what we would get for each of those intervals, which 0 to 80 all adds up to 24,640. So then it's that 24,640 divided by the 80. 308 meters per second. It's just kind of an interesting problem that does use what we're learning. Thought you might like it. Next, on the next page, we've got the second fundamental theorem of calculus. And this may just seem a little bit strange to you. We've got to have some things that work out for us. Before we do the second fundamental theorem of calculus, if you look down at the very bottom of this page, they're talking about this example 6, integrating from 0 to x of cosine of t dt at x equals 0, pi over 6, pi over 4, pi over 3, and pi over 2. And they've got all the different graphs with those different x values there. And at the bottom it says, you can think of the function capital F of x as accumulating the area under the curve for f of t equals cosine of t from t equals 0 to x. X equals 0, the area is 0. X equals pi over 2, all of it, all the way down to the very end, the area is 1. So the interpretation of an integral as an accumulation function is used often in applications of integration. So if we look at the next page, we see this second fundamental theorem of calculus. And this is just a nice little theorem if all of the conditions line up right for us. Second fundamental theorem of calculus says if f is continuous on open interval containing I, open interval I containing A, then for every x in the interval, the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. So there's 3 conditions that have to happen. The first off, we have to take the the derivative of the integral. So if we've got that situation going. The second situation, the integral has to be evaluated from a constant to a variable. Third situation, they have to be evaluating a function with a different variable. So if we're going from a to x, we have to switch the variable here that we're evaluating. If all 3 of those things line up, the answer is just the function at x. So I'm actually going to do example 7 with you. So it says evaluate the derivative with respect to x of the integral from 0 to x of the square root of t squared plus 1 dt. Alrighty, so let's see if what all's happening. I'm doing the derivative of an integral. Makes me think of the second fundamental theorem of calculus. I'm going from a constant to a variable. Interesting. And then our function is a different variable. So when all 3 things line up, the answer is simply the function evaluated at the variable. And that's it. I'm not going to do example 8. There's nothing wrong with it, but it gets into something called U substitution, and we're going to spend our time with that in the next section. So the last thing we're going to do is on page 296, called the net change theorem. So if capital F prime of x is the rate of change, so rate of change makes us think of a derivative. of a quantity f of x. So it is the derivative of this quantity, capital F of x. Then the definite integral of capital F prime of x from a to b will give the total change or the net change of capital F of x on closed interval AB. Shiloh, my dog, being silly. So the net change of the integral from a to b of capital F prime of x dx, we're going to integrate this derivative, and it's going to just bring us to this capital F. And we're going to evaluate it first plugging in the b and then plugging in the a. And that would be the net change. I just thought I'd remind you of maybe you've had a job and you had some paychecks, and your gross pay is the amount of salary you earn based on the number of hours you worked or based on your contract. So that's your gross pay. It's before any taxes come out. It's before any investments come out. It's before any insurance comes out or anything that you have. It's the gross. It's the top amount that you made. Your net pay is the part that you scoop up and you bring home after your taxes have been paid, after your insurance has come out, after your our 401k contributions, or whatever has come out of your paycheck. It's the amount that you're able to scoop up in your net and take home with you. That's your net pay. It's kind of similar to this idea of a net change. So it's the total change or the net change. And to talk about the difference here, we're going to look at example 9. A chemical flows into a storage tank at a rate of 180 plus 3t liters per minute. Don't read past that word rate. That's important. Where t is the time in minutes and t is between 0 and 60. Find the amount of the chemical that flows into the tank during the first 20 minutes. In other words, find the amount of chemical that has accumulated in the tank in the first 20 minutes. So that accumulation idea is an integral. So what they're wanting us to do is to integrate the first 20 minutes. So from 0 to 20 minutes of this amount, this function that they gave us, this 180 plus 3t, we're integrating a rate. So that brings us to this idea of the net change function, where a rate is a derivative. So when we integrate a rate, we're just going to integrate this function then. So it's 180t plus 3t squared over 2, and we'll evaluate it from 0 to 20. First, we'll plug in the 20. And then we'll plug in the 0. 180 times 20, 2 times 18 is 36 with 2 zeros. Let's see, 20 squared is 400. 400 divided by 2, 200. 200 times 3 is 600. So it's 4,200. So the amount of water that flows into the tank during the first 20 minutes is 4,200 liters. So that would be the net change. That's how much the amount of chemical in the tank changed from 0 minutes when it was empty to 20 minutes. It changed by 4,200 liters. Okay. And then at the very bottom of the page, it says another way to illustrate the net change theorem is to examine the velocity of a particle moving along a straight line. So this is a particle motion problem. This is sometimes called rectilinear motion, and it just means it is a particle moving along a straight line or a path. Moving along a straight line where s of t, that's our position function, is the position at time t, then the velocity, remember the velocity is the derivative of position. The integral from a to b of v of t dt. Again, if you notice here, we're doing an integral of a derivative because velocity is the derivative of position. So when this happens, when we take an integral of velocity, it backs us up to the position function, and we would do the position function evaluated at b minus the position function evaluated at a. This represents the net change in position. Or displacement. So a new word. The displacement of the particle. Alrighty. Top of this page. When calculating the total distance traveled by the particle, you must consider the intervals where the velocity is less than 0 and the intervals where it's greater than 0. So if you look at this little picture that they've given us, uh-oh. So we've got to consider the intervals where the velocity is less than 0. So that would be these areas where we're negative, and where we're greater than 0, where we're positive. And the particle is assumed to be moving from left to right. So we're moving along this straight path. Doesn't mean it's a straight line, it just means it's along a curve, moving along this curve from left to right. To calculate the total distance traveled, we would integrate the absolute value of the velocity function. So two different ideas here. The total distance traveled would be the path traveled. Well, it would be us integrating from a to b of v of t dt, and the area 1, the positive area would count, and then we would minus, and then the negative area would count because we're still traveling, and then the other positive area curve would count. All three of these paths would count because the particle's still moving. Even though it has moved to a negative velocity, it's still moving. So that would count. It's kind of like here, you're standing here, and then you take 2 steps forward, and then you take a step back, and then you take 2 steps. Well, I guess when you take a step back, then you're going to take 2 steps forward. Then you take a step back. Then you take 2 steps forward, and then you take a step back. But all those steps count because you're stepping. And if you have a step tracker, it doesn't matter if you're walking forward or backwards. All those steps count. So that's your total distance traveled. Doesn't matter if it's positive or negative, all those steps count. So it's that absolute value. But the displacement means how far are you from where we started. So the displacement for this little 2 steps forward, 3 steps back thing that I was talking about, I would only be able to count from here, to here. It would be like 1, 2, 3, 4 steps is all I would be able to count. When in reality, I took 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. Total steps. But the displacement, how far did I end up from where I started? That's what displacement's asking. How far did I travel from where I started? Well, just 4 steps away. So, total distance traveled is this formula where we're dealing with the absolute value. It didn't matter that this A was negative because we're dealing with the absolute value. But the displacement is the integral from A to B of V of t dt. In my positive area, I'll subtract that negative and then we'll add the other positive. So that's how displacement works. All right, example 10. The velocity in feet per second of a particle moving along a straight line is V of t equals t to the third minus 10t to the second plus 29t minus 20. You know what? Now that we've taken these notes, let's just go ahead and pause right here. And when we're together Wednesday, we will pick up here. And I'll show you how to integrate more complicated functions like this on your calculator. And we will work some problems using net change theorem and particle motion in class together Wednesday. Alrighty, I'll see you all in a few days.